Hello and welcome to the Institute of Microproduction Technology. My name is Rico Ottermann and today I would like to give you an insight into the manufacture of directly deposited thin film sensors for their use in bearings. In other videos we have already shown you some directly deposited sensors for other applications, but what makes it special here is that they will be used directly in the tribological contact. With these sensor-integrated bearings, it should be possible to measure load collectives and temperature changes induced by the rolling elements and other influences with a maximum information depth. At the beginning, the thrust bearing washer, our substrate, is polished using a grinding and polishing machine to create an absolutely smooth surface with low roughness values for sensor deposition. Next, the sensor production begins in our cleanroom using sputtering processes. First, a transparent insulation layer of aluminum oxide is deposited over the entire surface of the bearing washer. This ensures that the subsequent sensor layers are separated from the bearing washer by a non-conductive film. This is followed by the deposition of the two sensor materials, deposited in different areas with the help of shadow masks. We use Constantan for the strain gauges. It is ideal because it has an almost temperature-independent resistance. In other words, a very low temperature coefficient of resistance, TCR, close to zero. For the temperature sensors, platinum is used. It has a high TCR value, which enables precise temperature measurement. However, to ensure that the platinum adheres reliably, a thin layer of titanium is first deposited as an adhesion promoter. In the final step of sensor material deposition, gold is applied using another shadow mask to the outer area of the bearing washer, where the conductor tracks and contact pads of the sensors will later be created. Here, gold significantly reduces the lead resistance and allows for reliable contacting later on by means of soldering. Then, the sensor layers are structured. Using photolithography in the yellow light area in the cleanroom, a photoresist is applied and then exposed. After development, only the sensor structures are covered with the photoresist. In the subsequent ion beam etching step, the areas not protected by the photoresist are completely removed down to the insulation layer, leaving only the desired sensor structures on the bearing washer. It is a major advantage of the developed process chain that the etching process structures all layers simultaneously, since it simplifies photolithography on the complex substrate. After removing the photoresist from the remaining sensor structures, the contact pads are protected by another shadow mask. The sensors are finally coated with a transparent wear-resistant layer of aluminum oxide. This completes the production of the thin film sensors on the bearing washer. Now, electrical contacts are established by soldering, enabling the sensor characterization in terms of their nominal resistance and their TCR values. They are then ready for functional testing in the test bench of our project partner, the Institute of Machine Design and Tribology, IMPT. The integration of strain gauges and temperature sensors directly onto the bearing washer enables the load detection during the operation of the bearing. This allows for the implementation of an intelligent condition monitoring system in order to increase the safety and to reduce the downtime of the component. In the future, this sensor technology should be used in large diameter bearings, such as in wind turbines as well. With that, I would like to end this short introduction into one of our research projects. Thank you for joining us.